Okay, welcome everybody to our Friday session. Happy Friday. Um, so we want to pick up where we left off at the end of the last lecture, all right? And in order to do that, impulse is a really good connector. So we stopped, it was the last thing we did, and we'll review it to motivate our discussion of collisions today. That's what we want to do. And as we saw yesterday, that this impulse equation, right? It sort of looks like the equation for work, except that instead of being a spatial integral, it's a temporal integral. And what I mean by that is we're integrating with respect to time. I'm looking at force as a function of time. And you'll notice that our limits of integration give us the duration of the collision, okay? Now, what we found is that as complicated as this can be, and it can be complicated, one of the things that we interpret from our definition of momentum, if you remember, we define momentum as P equals, no, I'm sorry, F equals dp dt, right, where P is equal to mv, that's our momentum. All right, that's all we need to really remember from yesterday. We can define and see from the calculus relationship that the impulse will just be the overall change in momentum, okay? And what we saw is that we could come up with a simpler expression for our impulse by looking at not the complicated function to integrate over, but looking at the average force. If we could come up with an easier average force while maintaining the same area under the curve, then the impulse will just be equal to F average times delta t, right? And that'll give you the base times height, the area under the curve. And that'll give you the same thing. And one thing to keep in mind is keep in mind that the collision happens between the initial time and the final time, right? And as long as the area under the curve is the same, we'll have effectively the same impulse. Now, what we saw with our checkpoint, we're not going to do it again, but it's worth reviewing. We talked about someone falling, whether they fall on snow or the ground from an airplane. And what we saw is that, you know, we looked at the situation, right? So you have this person falling, and the ground becomes our period of interest, right? Right before the person hits the ground, we put our stopwatch going on. And why do we wait then? Because we're interested in the collision. So we want Ti to occur as close to the collision with the ground as possible. And then we can, you know, as soon as we stop moving, or the collision is over, or we are not interacting with the surface anymore, that's going to be T final. So these are going to be very short intervals in practice. And what we found is that, right, in the collision, J and delta P remain unchanged, but if the collision time changes, right, if the collision time increases, the average force has to decrease. And that's why if you're falling from a large distance and you can find either trees or snow, you can elongate your collision time, right? If you can elongate your collision time, you can greatly reduce the force on you. And in fact, being able to elongate the collision time from, say, a hundredth of a second to a full second, like that's all you need. And that will lower the force on you by a factor of 100. All right, so if it was 800 pounds of force, you know, like that you're looking at, which will kill you, you can reduce that to 8 pounds of force by elongating the collision time. So which is very survivable. So impulse can be a matter of life or death, which makes it exciting. But yeah. So we've got that. Now what we want to do is we want to sort of extend this a little lower. All right. So we want to look at a target, and I'm not sure the point of doing this for a stream of particles. I think that because we're really the meat of this and what I really want to talk about takes place in the in the bottom of the slide, which I absolutely want to talk about this stuff from below here. But in order to reference it and have it make sense, we want to understand the top of the slide that it's referring to. So if we have a steady stream of particles, right, that undergoes a momentum change that collides with the target, then you'll notice that J equals minus N delta P. Well, what in the world does any of this mean? So we know that J equals delta P, but where's this coming from? Where's these other terms coming from? Right? So we had before that J equals delta P, but now for the stream of particles, we have a minus sign and an N side, right? So the average force, if you look at it, you have your particles going this way. The idea is that they'll bounce back, right? So if we look at the stream of particles, that's usually what minuses indicate, is that things are changing direction. They could be stopping, but I guess they build up, and that would be against the spirit of the problem. Let me see here. No. So when we look here, it gives us that our F average is equal to our impulse over delta t. They plug in the N delta over delta t, where the N is just the number of particles, right? The N particles in our stream, right? And they'll hit this target and go back. Now, what I really want to talk about is the two cases: if the particles stop and if the particles bounce back with equal speed, right? So when we look at this, we can also look at an equivalent situation where we're dropping particles, right? Two seemingly identical particles, but one sticks to the ground and the other is like a bouncy ball, it goes up and down. Okay? And so if the particles in this situation stop, right, we have this delta V term where our final velocity is 0 and our minus V is, our initial V is V, so our net delta V is going to be minus V. And as you can see, when you plug that in here, you get a nice positive number for the average force. If the particle bounces back with equal speed, right, then you'll have delta V equals minus V is your final speed, right, minus positive V is your initial speed, and you'll have minus 2V, okay? So the real point here, besides worrying about where everything comes from, is that to note here is that there's more force. The average force is bigger when you bounce back than when you stay on the target, okay? So even though it can seem, and if you do the situation we talked about up here, right? If you look at it here, if you drop this ball, you'll hear a loud thud, and this would sound softer, right? So your intuition might tell you that this is a larger force. And if you think about it, I mean, if you hear me drop something, I'll drop some tape. It makes a loud thud, right? If I had something like this that bounced, it would make a much softer sound. And so you might think, oh, well, the thing that stuck had the larger force. But in reality, the momentum change is larger, and the average force is thus greater. Okay? So that's the big takeaway from here. Again, looking at things, we have the we have the number of particles, we have the momentum. All the minus sign tells us here is that the change in momentum is the opposite, which we can see is from here, right? Our delta P's will be in this opposite direction, and the impulse will be in the opposite direction of the change in momentum. All right, because remember, these are fundamentally vector quantities, so direction matters. Okay, so let's move on, and I think doing well, let's do the checkpoint and at least see why I forgot to erase the answers for this one. Oh no, I didn't. Yes, I did. Yes, I did forget to erase. Damn it. Crap. Oh well. So the product of the number of particles times the mass of each particle will give you the total mass for n collisions, so we can actually write it like this. So let's go back and look at and explore, you know, without worrying about n collisions. Let's just worry about a single collision again, because that's a little easier. So the figure here shows an overhead view of a ball bouncing from a vertical wall without any change in its speed. All right, so we want to consider a change delta p in the ball's linear momentum. So we want to see, is delta px positive, negative, or 0? Well, we have the answers, but let's at least try and understand them. So remember, when we look at this, j is a vector, and p is a vector, and force is a vector, right? So all of these have vector quantities. So if we're moving in the x direction, right, and we say that we collide with the wall, but the speed remains unchanged, we have to remember that the speed is going to be equal to the square root of vx squared plus vy squared. All right? So we want to consider our change in momentum. So if we look here, the figure shows this ball bouncing like so, right? Now, is the x direction going to change? Well, you'll notice that the x direction is still to the right, both before the collision and after the collision. In fact, the collision seems to only change direction in the x and y. And so if we have a collision, right, and our initial speed is maintained the same, we can almost, the easiest thing to assume is that the values, the magnitude of vx and vy, will actually stay the same, right? The square of them, if you will. But we can see here that, in fact, only the y component will change. So the x component will have 0 change, so that will be 0 change in momentum. Now, is py, is the change in the negative, is the change in the y direction positive, negative, or 0? Well, this isn't so bad, right? We start off with py as going down, and then that's the initial, and then we go to p final as positive, right? So we're going from, say here, -2 to 2. And I maintain that because when you square them, you'll get the same result, which will ensure that the speed stays the same. But you'll notice going from -2 to 2 is a change in +4. So the change in the y component is going to be positive. Now it asks, what is the direction of delta p? All right. So delta p, the change in delta p, we're going to see that if we look at our, right, p final minus p initial, we're going to notice that there's 0 change in the x direction and a positive change in the y direction. So delta p, we know will be equal to delta py in the j hat direction, right? That's it. And we already know that's positive, so we know that we are going to change along the positive y-axis. All right? And you'll notice it says normal force here. Why does it say normal force? Because remember, normal forces are normal to surfaces, and that's what you're colliding with. So you'll experience a brief normal force or a normal impulse, and that will change the y component of your collision. So it's a little less, it might seem a little less spectacular in this sense, but you know, these are sort of the nuts and bolts of momentums and impulses, and we'll get to the nuts and bolts of collisions. But I don't think that this is quite enough as far as examples go. So I want you to sort of marinate with what we have, and I want you to try and work out the next example, all right? So we have a race car wall collision, is in an overhead view of a path taken by a race car driver as his car collides with a racetrack wall. So just before collision, he's traveling at a speed of 70 meters per second along a straight line at 30 degrees from the wall. And just after the collision, he's traveling at a speed of 50 meters per second along a straight line at 10 degrees. So there's a lot to do here, and the key to solving this problem is to really interpret it. So they want to know, so his mass is equal to 80 kilograms, and we want to know, so just before the collision or just after the collision, he's facing the straight line, his mass is 80 kilograms. Is there a question in here? Did I miss it? Let me see. So the first question, I don't want to give away the question. I asked it on the next. So here's the given information. So before we even look at the question, I want you to try to sketch out this problem. All right? I knew I had a question in there somewhere. I just put it in a different place. So take a look at it and see, remember, what we're really focusing on is drawing everything out. So I'll give you a minute or two, and then we'll go over the drawing, okay? Mm-hmm. Oh, people are drawn. So that's where all these other drawings come from. They come from you guys. That explains some of my craziness. Okay, that's not terrible. Yes, Mina.
I tried.
I think my orientation issue is the so let me see. Yeah. I mean, it's just I think I would have just done it the other way, only because I'm going to cheat a little, and I've taught it before, and also I have this nice barrier. So I guess how I do it is the only thing where I think I get confused is your theta 1 looks like your theta 2, even though you've correctly drawn them the same. So that should help you. The problem is when you draw it, get an idea of the vector, that's where things will be an issue, right? Because that's the first step. So I'm going to use the green border between the blue segment and the white part as my wall. So if I have a line, if I have a line, right, I'd go up here, and then, and having straight edges helps because we want to be able to see the difference, right? So here we have theta 1, theta 2. So like I said, not bad, or that's theta 1. And this one would be theta 2. I mean, you know, it's a good try, but now we have to look at some other parts of this as well, because we have the initial part, but the next step is drawing the vectors. So I'm going to make one more line for my y-axis so I can get that. I want to get the axis right. All right, so that'll have to be good enough. So let me change colors here. So one thing we can see from going from here is at the collision point, right, we have our initial momentum. So that will be pi. And then we'll have our final momentum. Pf. And when we look at this, remember J equals delta P. And so in this particular problem, we won't have to do a lot of integrating, but we'll have to do a lot of vector addition. So in order to sort of get an idea of where this will be, right? Nope, that was the wrong one. And now I'm going to pay the price by having to delete all these little dots. So remember, delta P is P final, which we have here. And then we're going to have to make an auxiliary vector. So we have Pi. This will be minus Pi, right? So Pf minus Pi will get you something, depending on which one's bigger, very likely in this quadrant, all right? So that would be delta P. But we'll verify that. And as you can see with the picture, we can sort of see that that's exactly what will happen. Is we have P final, right, minus P initial. So we make that go the other way, and then you already sort of see one of the answers, but you'll see that J is going to live in that third quadrant. And it's important to know what quadrant your vector is going to live in, because when you take the arctangent, you'll have two solutions, and if you just write it down blindly, you may be in the wrong, you may be off by 180 degrees. So the first thing we want to know is, what is the impulse on the driver during the collision? Well, we already see how that's going to kind of work. So let's go back and look at, knowing that that's the question, let's go back and look at our problem. Okay? So we know, we have a set of known stuff. So we know just before the collision, VI is equal to 70 meters per second, right? And we know it's at an angle of 30 degrees. And you might be wondering, well, wait a minute, Professor Toland. Isn't it 30 degrees from this part of the wall? This is true, but we're constructing momentum vectors, right? So when we look at the momentum vector, we're going to look at this vector, which is 30 degrees from here. And what value are we going to, if we're going to call this 30 degrees, what value are we really going to use for theta? Are we going to use 10 degrees? What number are we actually going to put in when we break up into components? No, you're all breaking my heart here. Hurtful. Hurtful. No. If this is 30, make me have a sad weekend. If that's 30, are we going to call this 10? What angle will we really write out when we're evaluating our trigonometry? I'll give you a hint. 10 degrees. Yes, Mina.
Sorry. Can you repeat the question because I got confused?
Yes. So I'm asked, basically what I'm saying is when we look at this initial momentum vector, right? We're looking at where we can use that from this actual vector, it makes a 30-degree angle with the x-axis. What I'm really asking, and I think someone got it right, is what angle does the final momentum make from the x-axis? Is it positive 10 degrees? Yes.
So if there's going to be minus 10 or 360 minus 10, depending on how
so
you
So minus 10 will be a little cleaner than 350, but either works. But yeah, you can just call this minus 10, okay? Once you set up the problem from here. So then when you look at this, you have px equals m vx, right? And py equals m vy. And so this will be equal to m v cosine theta 1, or cosine, cosine theta, and this will be equal to mv sine theta. And it just depends on whether we're talking about the initial or the final, what that value of theta is, right? So let's set the problem up symbolically, and then we'll go back and look at our numbers, because there are too many numbers given. And basically what we'll do is we'll set up the problem, and we'll make a list of what's given and then see if it's given. I think I like that better. That's a good idea. I like that idea. So let's look at the initial momentum vector first. So we have here pi x equals m vix cosine theta 1, right? And p final x equals m, this is supposed to be an x, mvx final cosine theta 2, right? We have theta 1 and theta 2, so we already know that's not going to be a problem. And so we can look at the x component first, right? We can pf minus p initial in the x direction will give us m times v final cos theta 2 minus v initial. And these, of course, are in the x direction. Oh, no, these are magnitudes. Sorry. See, now I'm getting the Friday blues. That's true for the x, but these will be magnitudes here, right? Because we're taking the component. So that'll be v final minus v initial cosine theta 1. All right, now if you recall in the problem, I don't want to slip away from it, so I'll just go to a version I have in front of me here. If you recall, we are given v initial. We know we have both of the angles, right? We can see that on the picture. We're given v initial, and we're even given v final, and we're given the mass. So we can definitely find delta pix, and by extension, we can then find j of x, right? So all you need is to do is plug in those numbers and you can get it. And similarly, we can see that pfy minus p initial y in the y direction, right, will equal m v final sine theta 2 minus v initial sine theta 1, and that will equal j of y. And if you want to get the impulse, the total impulse, right, j will be equal to jx in the I hat direction plus jy in the j hat direction. And if you want to find the magnitude of j, which you may want to do, you can just use your Pythagorean theorem. Okay. So that will give you that. If you want to check your answer, you can, the correct vector is j equals minus 910I minus 3500J. And of course, in kilograms, meters per second. Okay. And again, our vector addition is consistent with this because we have, you'll notice when we did this, we suspected we'd be in the third quadrant, maybe the fourth quadrant, but somewhere right here. So that's pretty consistent with what we have. If you want to take the tangent and find the magnitude and angle, you can do that on your own. That's a good exercise to review that skill. If you're wondering how I got these components, this is the point in the semester where if you haven't done any of the vector marathon extra credit, I highly suggest you go back and do some of that because it's been a few chapters since we really dealt with vectors. So I would go back, and I'm expecting you to know all of that stuff. This is a great time to revisit that. And not only refresh your knowledge on vectors, but to get some extra credit as well. Okay? So, any questions on this exam, on part A? Nope? Good. So now let's move on to the more exciting part, which is part B. So the collision lasts for 14 milliseconds. What is the magnitude of the average force on the driver during the collision? Well, I'm just going to give some of this away. So the magnitude of J from the last part, which again is just algebra on your part, right? The magnitude of J is going to equal 3,600 kilograms meters over seconds. And so we want to know what is the magnitude of the average force. So we know that J equals F average times delta T, right? So if we solve for F average, thankfully this part B is easy, but part B is a little more interesting, right? Equals J over delta T. And we get that the average force, when we divide those numbers, is about 2.6 times 10 to the 5th newtons. Okay? So this is sort of exactly what I was meaning to show you. So that's 260,000 newtons. All right? Now, if you can increase the collision here to even a factor of 10, right, and make this because remember T here is equal to 0.014 seconds, right? That's 14 milliseconds. So if you can even increase this by 10 times, you'll get down to 2 times 6 times 10 to the 4th. You know, you lose 90%. The force, I guess you could say, you know, your reduction is almost an order of magnitude on the force that you're feeling. So if you could get this up to a second, this becomes quite a bit less. You know, a force of 260 newtons for a 1 second collision or 1.4 second collision is substantially less than you know, 260,000, right? So when you're making you know, increasing collision time, particularly in contact sports like around the head, this has been a big area of research, and it's very profitable. particularly for car safety. For instance, that's how airbags work, right? So, you know, when you're in a car and you stop short, if you hit the steering wheel with your head, that's a very low collision time. The whole thing an airbag does is it makes that collision go from about 14 milliseconds to about half a second. Okay? And so now you have so because you've gone from 0.014 to 0.5, the force on your head is substantially reduced. And you might get a concussion, but you won't get a cracked skull and die. So airbags, that's how airbags save lives, and a lot of applications for this topic in particular, and collisions in general. We're always bumping into things, and we always want to try and survive. So, any further questions on this example? Good stuff. Take a while and let it stew. All right, we're okay here? Okay. So let's move on. And we're going to now move on to conservation of linear momentum. So you'll remember we've talked about systems of particles, and we've been using that language when introducing sort of center of mass and momentum itself. And much like when we introduced energy, we made a point to talk about systems. And so you'll notice that if we have a system that's closed and isolated and the impulse of 0, all right, so if the impulse is 0, that means J or P is equal to constant, right? And the result here is that if no external force acts on the system of particles, the total linear momentum of the system cannot change. Now, this is going to seem counterintuitive because an impulse, right, is seen as something external to the system of particles. So we'll have collisions, and you'll say, well, wait a minute, those two things are colliding, but those will be looked at as internal collisions. So like if two cars hit each other, and you know, we can actually, I think it's easy enough to add with friction. But if we have two objects collide in a vacuum, you might be tempted to say, well, that's an impulse. It's not an impulse if it's an isolated system, right? The impulse acts as an external agent changing our system, all right? So when we set the impulse equal to 0, it's not that things can't collide and change direction and have it look like that, but when we talk about a collision, we're saying, well, we can set up a system in which there's only internal effects between the objects in the system. So that context, even though subtle, is going to lead to us to say that if there's no external forces acting on a system and associating collisions with external forces, yeah, this thing has invaded my computer, and I need to get rid of it. It's like I have Windows Defender. I don't need this thing. No, I had to download some hard drive utilities to learn about merging partitions, and then it had a bunch of other crap that came with it, so not good. Anyway, that's neither here nor there. I trust Windows Defender to actually find things that are wrong with my system, so I don't need to pay money to do the other things. So anyway, back to this. So again, the impulse is associated with an external force, but you can still have collisions with internal forces. But if everything can be described internally and the system is isolated, right? Then in that sense, P or momentum is constant and it will be conserved. All right? So that means that much like energy, we can look at a system and have that the initial momentum of the system is equal to the final momentum of the system, right? But keep in mind that for a system of particles, for instance, right, that could imply that you have P1 initial plus P2 initial plus dot, dot, dot equals P1 final plus P2 final plus dot, dot, dot. So that means that the individual momentum can change of each of these, right? But when you add them up, you're going to get the same thing. And then when you add up the initial side, it's always got to equal the final side. All right? Now, this is covered. That's not great. Didn't create right. So you want to check the components of the net external force to know if you should apply this. All right? If the components of the net external force on a closed system is 0 along an axis, then that component of the linear momentum of the system along that axis cannot change. All right? So basically, you can have momentum conserved axis by axis. And you only need it conserved along one axis to apply it for that axis. I believe it need not be conserved on the other axis. All right? Pretty cool. Vectors make things complicated. Yeah, Mina.
So if we have a problem with analysis of three dimensions, as long as we have constant one dimension, either y, x, or z, that means we can work from there on to the rest of them, right?
No, that's exactly the opposite of that. You're only assured conservation on an axis-by-axis basis. So once you do it for y, you know that momentum is conserved in y, then you have to prove it for x, then you have to show it for z. So it's possible, for instance, to have a j vector, right? We can have j equals 3i, and that's it, right? Plus 0j plus 0k. So momentum is conserved in these axes. Momentum is not conserved in the x-axis in this particular case. Okay? I don't know if it makes sense, but I'm hoping that that part is clear. Exactly. That's it. That's a good way of looking at it, Nicholas. Okay. No, I can tell you we don't cover Hohem transfer orbits, etc. Physics 2 covers electricity and magnetism. So basically this semester we build the basics of physics and we talk a little bit about Kepler's orbits and stuff like that. But anything beyond that is intermediate mechanics. And then next semester we build up Maxwell's equations to describe electromagnetic theory. So that's what we do there. Physics 2 is not a continuation in a classical sense of this course. It's not a more advanced version of this course. For that, you need upper division physics, and that is hard. You know. So, I guess you could say we're just covering the basics. So again, I made this point, but it's worth repeating that the internal forces can change momenta of parts of the system, but cannot change the linear momentum of the entire system. And this is the big one. Do not confuse momentum and energy. They will be needed to be used in conjunction frequently, but you have to be able to tell them apart. And that's actually kind of the whole point of the next set of labs, the conservation project, is that you'll be looking at energy conservation in that sense, and you'll have to look at when to use energy, when to use momentum, and how to not confuse them and when they apply. Because remember, momentum is, they're completely different quantities. Momentum is a vector and energy is a scalar. So let's take a look at this checkpoint and see if we can make some sense of it. So an initially stationary device lying on a frictionless floor, notice we're still a little scared of friction, explodes into two pieces, which then slide across the floor. So that's just going like this. One of them in the positive x direction. So what is the sum of the momenta of the two pieces after the explosion? B, can the second piece move at an angle to the x-axis? And C, what is the direction of the momentum of the second piece? Okay, so this should be, think about what we just talked about this specifically. So relate our discussion about conservation and directions on axes and see if you can figure this one out. So I'll give you a minute and then I want to help you with part A. I think B and C might be easier. A might be a little counterintuitive, but it's super simple. It's right there. The answer is staring you in the face. Okay, so hopefully if you had a hard time starting with part A, remember that when we talk about the system, it's really just important to look at the words, right? So we have a device, that's going to be our system. It's lying stationary on a frictionless floor and explodes into two pieces, all right? So the question is, what is our initial momentum, right? So there's no external forces. Very good. Good, Mina. No external forces. So our initial momentum, right, is going to be equal times m the initial. The initial is 0. And so our initial momentum is 0. Now the conservation of momentum says that the total momentum of the system, P final, has to equal P initial, and therefore must also equal 0. Okay? Now to understand what this looks like, you have P object, right, equals P of 1 plus P of 2. We don't know anything about these yet. We're just being very general. So we can see here that this has to be 0, and then we have to see that these will also have to be 0, right? 0 has to equal 0. So the sum of the momentum of the two pieces after the explosion has to be equal to 0 because the initial momentum is 0. Okay? Yes, so A is 0. Does that make sense? Does everyone see it? I know Mina sees it. Good. Now, can the second piece move at an angle to the x-axis? Now we talked about this extensively. I was hoping part B would be the easiest part, that you'd read that and be able to answer it right away. Because we just had a question about this. Right, it can. right? We know it moves along the x-axis, and momentum is conserved on the x-axis. There's no external forces, so momentum is conserved in the y-axis as well, and there's no momentum in the y-axis. If we're moving in the x direction, and momentum has to be conserved in the x direction, that's what we're limited to. Okay, so there can't actually be an angle. What is the direction of the momentum of the second piece? Negative x. Good. Right? And we can see that. All right. Very good. Okay. Now, as we can see, we're correct. So now we have a little bit more fun to do here with a two-dimensional explosion. All right. So now we're looking at this from the top, from a bird's eye view. So this is sort of similar to the checkpoint, but a firecracker is basically placed inside a coconut of mass m. Initially, it rests on a frictionless floor. It blows the coconut into 3 pieces that slide across the floor. And an overhead view is shown in this figure, right? And piece C has a mass of 0.3 m and a final speed of 5 meters per second. So what we want to do is we're going to want to figure out what the final speeds of each of the next 2 parts are. All right? So we're going to want to figure out the final speed of piece B and then the final speed of piece A. All right? And in order to do this, you're going to have to make some, creative selections of your axes. And you'll notice they kind of do it here for you. If you pick your axes right, you can eliminate one of your variables. And you'll notice that when you select, oh, they used purple. I have to use a different color. I'll use blue here. You'll notice that selecting this x-axis means that even though we have seemingly too much to know, only B and C have Y components. We know everything about C, so that lets us solve for B immediately, right? And then once we solve for B, then we can include and solve everything for A. So I want you to try working on that. I want you to try working on that on your own. What we're going to do is we're going to go on break now until about 10 after, and then we'll come back and we'll start with how to do this. So actually, I might give you till 15 after, 5 minutes to work on it, 15 minutes for break, and then you can you can work on it through break if you want, and we'll go over it after break and see how this works. Okay, so see if you can set it up, and just try playing with it. The point is to either have questions or to get stuck somewhere, and then as I go over it, hopefully it'll clarify where you get stuck or help you form a question, and then we can go from there. Okay. All right, so it's always weird to watch me just sit here and watch me while you work. So I'm going to turn off the video, and I will be here on microphone for the next 5 minutes, and then I will, or till 2, and then I will go. I'll go on break at 2 and be back at around 2:10 or 2:12. We'll resume at 2:15. Okay, but I'm here to answer immediate questions you have about this right now. All right. I'll be back. All right. So, anyone get it? Well, I'll just go. Let you type and tell me. So when we're looking at something like this, that's okay. You can work on it, and you can mute me on your computer if you want and come back and look and see how you did, or you can follow along, whichever one is fine. So we've got these three pieces. Now you'll notice this would be the given information, right, with these angles. And again, we pick this axes, these XY axes on this figure, to pick a system in which we can actually eliminate one object from our calculations, right? Because we have two unknown speeds. So what I mean by that is we can just look at the y components from the x-axis, which you can refigure out from these given angles. And you can just look at the y components. So let's look at that first here. Let's look at the momentum in the y direction. So we know that P, oh, wait a minute, let me change colors. I'm going to work up here. So we know that P initial, right, is going to equal 0. And that means that has to equal P final. But right now we want to concentrate on the y direction. So Py will equal, and we want to go around. We know Py initial will also equal 0. But, and I'll make a semicolon here, Py final. So we just want to go around and look at the y component of each of our momentums. And we'll start off with VFA. This is 0, right? So we have 0. And you'll notice we go here. We have our speed we want to solve for. Or not that we want to solve for. I think we're actually given VCF, right? So we're getting with our information. So we'll have that's going in the positive direction. So we'll say plus MC, right, times VC final, or VC. The final is indicated because the initial, there are no parts in the initial velocity, right, or in the initial momentum. The initial momentum is just the whole coconut. So VC, and then we'll notice we're in the minus y direction. So that's going to be VC, though, sine of 80. And that's going to be minus M B VB sine of minus 50, right? So when we look here, we can make some replacements to make the problem easier. Plus, here we have 0.3 M. And if we look at part A, which I didn't go to yet because I'm solving the problem here, but you need MB is equal to 0.2 M. That was probably missing. You do have that, but you have MC. So if they give you for part A that 0.2 is there, and then you can immediately see that a consequence of that is that MC must be equal to 0.5 M, right? So we have 0.3 M, and we have here for VC 5, right, times sine of 80 minus 0.2 times the speed we're looking for, sine of minus 50. So as you can see, we have one equation, right, with only one unknown. Actually, I don't like writing that there. It makes it look like it's something. But we only have our one unknown here. Okay, so this lets us solve for our p in the y direction pretty straightforwardly. Does everyone see that part of it? Are there any questions on what I did so far? The only thing you were really missing was that MB, but you know, that's okay. That might have been where a few of you got stuck, is having those two equations and two unknowns. So MB would have to be given to find this VB, and it is in part A. I thought I flashed it, but I did not. I remember that now. So okay. And so now to find, yes, so so M, the way to write this and to see it is that M is equal to MA plus MB plus MC. So each of these is given as a percentage of the total mass. So MA is given in the problem as is equal to 0.3 times M, and MB is also given, which you didn't see, it's on the next slide, as 0.2 M, okay, of the total M, that is the total mass. Yeah. Okay, so now in order to find VC or V of A, right, we want to find this third part. We can take a look there. I'm going to clear all this in 3, 2, 1. All right, so now to look at the third part, we just have to look at the X component. And you'll notice each of these has an X component, but now that we've done part A, we now know everything to know not only about C, but about B. So when we do this, when we look at our that sounds about right. Let's see. So yeah, VB is about 9.6. So anything around 9.6 is correct. So now, when we want to get that magnitude, we can do the same thing. P initial in the X direction is going to equal 0. So we know that P total final in the X direction also has to equal 0. But we can also write this as MA VA, which we're looking for, right? And then we can look at B, and that's going in the positive X direction, so that'll be plus MB times its VB cosine of minus 50. And we have also, or actually, this should be a minus sign, right? Because that's going in the negative X direction. So then we have plus MC, the final C, cosine of 80. All right, so we know all of these things except VA, right? And so we just now have one equation, one unknown, and we can solve for VA and readily get the answer there. And the answer there, if you're wanting to check it out, for the A piece is 3.0 meters per second. That is the speed of the of piece A. Okay. So we are now going to enter the wide world of collisions, all right? So now that we've talked about momentum, like we sort of do with all our chapters, we're now going to we've incorporated vectors into momentum, and we're now going to incorporate energy into momentum, and then be able to describe collisions, okay? So we still have a few examples to get through here. I'm not sure how far, we still have plenty of time, so we should make it okay. We'll see. I'm okay not finishing this chapter today, but we're making pretty good pace, so we'll see how it goes. But I'm not in any rush, I guess is what I'm trying to say for this one today. There may be chapters in the future where we are in a rush, but this is not one of them. So we have to look at our types of collisions first, all right? So you'll notice we have three. We have elastic collisions, we have completely inelastic collisions, or completely inelastic collisions, completely elastic collisions, and then inelastic collisions or intermediate inelastic collisions where some energy is transferred, all right? So these ones we're pretty much going to ignore. I mean, you might have one or two problems, but almost everything will be completely elastic or completely inelastic, all right? So let's go through and at least define each of these types of collisions in a way that makes sense. So each type of collision will be described by how much energy is conserved in the collision. So in a total elastic collision, total kinetic energy is conserved, all right? So in these collisions, momentum and energy are conserved. And in fact, momentum is actually conserved in all of these collisions. But total energy is conserved here. It's actually a useful approximation for common situations, even if a little amount of energy is lost. In real collisions, some energy is always transferred, but you know, if you're getting good rates, it can be very useful. Completely inelastic collisions happen when the objects stick together and they represent large losses of kinetic energy. All right. So, and then intermediate collisions, they might look like elastic collisions. They might bounce off. They might not stick together, but a lot of energy might be lost in the collision. So for the purposes of our class, we're really going to focus on elastic collisions and completely inelastic collisions. All right. But understanding both of these will help us understand and be able to handle inelastic, some energy is transferred, intermediate collisions, but we won't really do that. Okay? So let's go and have some fun with it. So for one dimension where we can keep things simple, in inelastic collision, right, we already talked about these, the objects stick together. So when you're talking about collisions, you always want to start off with the conservation of momentum. Because remember, P initial equals P final will always be true regardless, Jesus, will be true no matter what type of collision you have. Okay, thank you. So my throat's bothering me a little bit. So actually, I'm gonna get a cough drop really quick because my throat is bothering me a little bit. It's starting to make it hard to talk. All right. Oh, I didn't turn on my video so you could all see my face. Not that I don't know that matters so much. Okay. All right, here we go. Cough drops. Oh, that's better. Okay. So we always want to start off with momentum being conserved because that's always what we're starting with. And you'll notice that this term is an expansion of the initial momentum, and this term is an expansion of the final momentum. All right, so this is true in general. Now, in an inelastic collision, the objects stick together. So if you start off with two objects, right, and they go towards each other, but then afterwards they're one giant object moving in some direction, essentially you only have one object. So you don't need two terms anymore. You can combine this into one velocity term by adding the masses and recognizing they have a final velocity. This is a good example of reducing something via physical arguments rather than mathematical ones. You have to look at the argument, and there's no, by recognizing the physical situation, you can reduce the equation here, right? But there's no math step that says, oh, well, obviously these are the same. You have to recognize that, and then once you recognize that, you can have a reduced equation, okay? So that's how you get this. Now, we can further simplify the other side if we're firing a body at a stationary target, right? So if we have so that makes, so if it's a completely inelastic collision, they stick together and we get this target. But if the object's at rest, if object 2 is at rest, then this part goes to 0, and you only have this simplification here. So, taking away all that sort of craziness, ta-da, we can see that for any inelastic collision, the most general equation for the dynamics are given just by our conservation of momentum of the objects in the system, right? And all we care about is before the collision and after the collision, all right? We can actually ignore the collision itself, just as long as we see what things look like before and after. But our most simple case of this will be a object, right? A projectile hitting a stationary target and then them sticking together, okay? So our first, so let's sort of get, so let's break this down. I didn't realize this here. So for our general case, we can see we can have each body having some initial velocity. They can even be going towards each other, right? And then they'll collide, and afterwards they'll have final velocities, right? Both are moving. And you have this general equation. But now here we have our simplified situation where v2 is equal to 0. So there's only one term in the initial velocity, right? That's right here. And then in the completely inelastic collision, they stick together, and you have m, and they have a common velocity, all right, which we have with that v there. Okay. So, any questions on this? Does everyone see the difference? I'll make it a little more explicit. This equation goes with this figure, and this equation goes with this set of figures. Oh no. Oh, okay. Okay. All right. Okay. All right. So you'll notice that the center of mass velocity will remain unchanged from a collision. If we look at this, if we look at the system we're looking at the completely inelastic collision. So if we look here, you'll notice that the velocity of the center of mass, that will remain the same throughout the process. All right. Now, of course, the position will they'll sort of meet at this center of mass. It'll stick and become that that point where they both meet. But you'll notice that both of these, as they move towards each other where they meet at the center of mass, and then they stick together. All right? And the velocity at the center of mass is equal to the momentums, the sum of the momentums over the masses. All right? Or P over M. Let's do a checkpoint here. So we have body 1 and body 2 are in a completely inelastic one-dimensional collision. So we want to know what is their final momentum if their initial momenta are respectively 10 and 0, 10 and 4, 10 and minus 4. Okay? So when we look here, this should be pretty straightforward. Because remember, they have in any collision, right? We know that, I keep wanting to write deltas, but we know that P initial has to equal P final. Okay. So we don't, so to alleviate confusion, we're given the initial momentum, we're given P1 initial, P1 initial and P2 initial, right? For these set of problems. But it's not asking for P1 final and P2 final. That's not what's being asked for. It's asking for the system momentum, the final momentum of the system. That you should be able to find pretty readily. So for instance, we can see that the initial, since we have the initial momentum, P initial of the system, for A is going to be equal to 10 plus 0, or 10. And so therefore the final system so now you try B and C. Good, good. 14 and 6. All you have to do is add them up. 10 plus 14 gives you 14. 10 minus 4 gives you 6. The initial momentum must equal the final momentum. And there you have it. Now, our next, this is going to look like a Physics 2 slide. Physics 2 slides tend to be very busy very quickly. But this is actually, I think, one of my favorite examples to do in this entire class. So this is a big moment for me. So we have here an example of a common technique in physics. Sadly, it's not a common technique in this class, but it really is a common technique in physics, which makes physics in some ways much more difficult than your standard math class. So we have a demonstration that cannot be worked out as a whole, meaning we don't have a workable equation for it. So we break it up into steps that can be worked out separately. So we have equations for the steps, and then we match the equations where they can be matched, and then go our separate ways. What we don't have is one equation that solves the problem. And you know, it's actually kind of interesting. Do you remember the problem we did the first day, where we have the where we figure out the radius of the Earth from the sun setting? Does anyone remember that problem? Where you know that we looked at, we had a person get up? Yeah, so, and this is sort of what I mean by that. So my brother has been taking graduate level math classes for about, well, advanced mathematics and graduate level math. And he's convinced that physics is going to be super easy because it's applied math. And I told him, I don't know, man. I said, we ask very difficult, using very simple math, we can ask very difficult questions. So I gave my brother that problem about a year ago, and he was stumped for a long, long time. And he had taken 4 or 5 years of like really advanced math. And so I've been trying to explain to him that the skill set is different in physics, and that's why I do that problem the first day, right? Is so you can see that the math for that problem was super simple. If I set it up for you, all of you could do it like that. But that's not the skill, right? The skill is in setting up the problem. So, I mean, he did get it, but it took him a long time. In fact, it took him, with all that math, I would say a little longer than it took you guys to do it. For one of the principal reasons is that in the engineering world, you already sort of have more of an applied setup, right? And some of you probably have taken some engineering or even some chemistry classes. And he's never taken any college science classes, or at least not for 25 years at this point. So it took him a while. And he's not a dumb guy. I mean, he's pretty good at that kind of stuff. And my point for that, or telling the story, is to illustrate that it is a different skill. Like, we're learning, we use a lot of mathematics, but setting up the problem is the skill we're really working on here, not solving the problem. And this is this example of the ballistic pendulum is really a great example of that. So the ballistic pendulum was used to measure the speeds of bullets before electronic timing devices were developed, all right? And the version shown in the figure we're about to see consists of a large block of wood of mass equal to 5.4 kilograms hanging from 2 long cords. So something like this. I mean, we'll see a nice picture of it, but I want us to be able to do a sketch and understand the picture. So something that looks like this. Okay? And the question is, if you fire a block into it, how can you determine how fast the bullet's going? Now, a bullet of mass M of 9.5 grams is fired into the block, coming quickly to rest. So we're going to have what looks like an inelastic collision, right? The block and bullet then swing upwards, their center of mass rising a vertical distance of 6.3 centimeters. So before the pendulum comes momentarily to rest at the end of its arc, what is the speed of the bullet just prior to the collision? So not only do we have to pull from our math library of knowledge, but we have to pull from our physics library of knowledge. So 2 things happen. And like I said, there does not exist a single equation which solves this. You have to recognize that this is a 2-step process. So there's going to be the bullet going into the block. And then there's going to be the block, once the bullet is in, raising up, right? Swinging up. So we're going to be able to expand on this. So there are 2 events here, right? The bullet collides with the block, and then the bullet block system swings upward by h. So let's take a look at each of those. So here we have the bullet colliding with the block. That's one event. This is a collision. And then we have the block. Hold on. I keep drawing that wrong. I just get so excited by this example. We have the block raised by some height h. So you'll notice that here we have a collision. Here it looks like after the collision we have an energy problem. Now here's the thing here. Here's where not to get confused. Energy is not conserved in this collision, but we don't care. Momentum is. After we're looking at energy conservation after the collision, the bullet and block are no longer colliding. It becomes a different problem. All right? So we have 2 composite problems. We have a collision problem and then we have an energy problem, and we're going to have to see how we connect them. So I'm just hoping I don't give too much away. I want to just be sure I don't give okay, good. I don't give too much away. So this is a nice picture of the whole system, where we have event 1, and then we have event 2. And we're going to have to figure out how to connect them. So how I like to solve this problem, I love to start with what we're looking for, right? We want to know how fast this bullet's going. That's what we want to keep track of. So when we're doing that, we can say, okay, I know I have a collision here, and I have my bullet in that collision. So I have M bullet, V bullet, which is what I want. So this is exciting. All right. And plus the mass of the block times the velocity of the block, right? These will be the initials. And we know they're going to stick together. So that will be equal to M block plus M bullet times V system final, right? I can call that V system because it's combined and it'll be stuck together. So I'll just call it VS, but you know, we can call that final if you want. But it becomes one. It becomes one thing. All right. So now when we look here, we can measure both of these masses. So those are pretty easy, right? And we have here the block, the big M here is stationary, right? They're writing big M. I'm just trying to be a little more explicit with my BL subscript. So, but the block is stationary, so this whole term goes to 0. And I'm going to use, so I can write here that M, I'm going to use little m and big M. We'll see if it, no, I'll be consistent. MB V bullet, right, initial, that's going to equal MB plus big M BL times V system. All right, now I still want this initial velocity, but you'll notice I'm missing the system velocity. So I have 2 equations and 2 unknowns, but it's an inelastic collision. Energy is not conserved, so I'm not getting anything out of that way. And there's only one component here, so I'm not getting anything out of there. So it looks like I'm stuck. But now we can go to event 2, which we'll do in orange, right? We can analyze event 2. And in event 2, once the block is moving, we can look at it, and with you know, assuming that there's very light friction here, and there is, like the time at which this is happening, the friction won't contribute much of the hinges. We can look at this as a conservation problem, right? Because the only force that's acting after the collision, so the collision's done now. When we look at event 2, the only force that's active is gravity. So in that sense, energy is conserved, and we can, because all we have is a conservative force. And so we'll note that we have 1/2, hold on, I'm skipping steps. Skipping steps is bad. So in this sense, we'll have our kinetic energy plus UI equals K final plus U final. Now, a few things to note. Initially, down here, we're calling this position, right, y equals 0. So in that sense, initially, there will be no potential energy, and everything will be kinetic. So we'll have Ki, and then once we get to the top, this is the maximum height, so that converts all that kinetic energy to potential energy, so K final will be equal to 0. And, yeah, sorry about that. I live next to a hospital. And then we'll have this equals to U final, right? Now, looking at these, we have this is equal to 1/2 m v initial squared equals m gh, right? Where you'll notice that here I've been a little sloppy, right? So this m is the system mass, but I get to be a little sloppy because these m's are going to cancel, right? And you'll notice that you can get here, this implies that VI equals the square root of 2GH, which is our common result, right? Now, here's the interesting part. The initial velocity of our second event is going to be the final velocity or the system velocity for the first event. So what I can do is I can say, I can recognize that physically, right? Saying that the velocity that's starting will be due to the collision. So in that sense, I can rewrite my mass of the bullet. I can go back to red. I'll do it in green. Now I'll do it in blue. So now coming down here, I can combine these two events or connect them where they matter, and I can say that I can say that MB VB initial equals M block plus M bullet, right, times the square root of 2GH, right? And now this is all known, and we know we now have a solution here, and we can write that VB initial is equal to MB or MB plus MBL over MB times the square root of 2GH. Okay? And that's how we can solve that problem. But again, we have to construct our model, because this is really a model, our solution from applying the conservation of momentum at one event, right? The conservation of energy at another event, and recognizing that the velocity, the initial velocity from our kinetic energy will indeed be one and the same as the velocity from our momentum problem. All right? Pretty neat, huh? So does that make sense? Any questions about this example? That's okay. That's why they're recorded. Rewatching the video is why they exist. Okay. So I think if we're good there, we can move on to elastic collisions. All right. So when we look at elastic collisions, unlike what we had before, so we're gonna again look at a simplified case, right? So in an elastic collision, the kinetic energy of each colliding body may change, but the total kinetic energy of the system does not change. So in a completely elastic collision, right, or an elastic collision, not only is momentum conserved, but kinetic energy is conserved. And what we've done here is we're looking at the special case again where we have a projectile hitting a target. All right. So what they've already taken the liberty of canceling out the momentum terms of the initial part here, right? Since that velocity equals 0, you have no second term both in momentum or energy, right? The kinetic energy is clearly 0, and the momentum is 0. If you don't believe me, or if you want to see it, remember that P equals mv. If v is 0, momentum is 0, and K equals 1/2 mv squared. So if that's 0, then kinetic energy is 0. All right, and that's where we get these terms here. Now you'll notice at the end they don't stick together; they each have their own individual speeds, right? So there are 2 terms at the end here. And we're going to see that this can get kind of complicated very fast. So with some algebra, which I'm not going to do because algebra is awful, you can get the final velocity of each in terms of the initial velocity of each, right? So you can get v1 in terms of v1 final in terms of v1 initial. You can also get v2 final in terms of v1 initial. And again, keep in mind that that v2 initial is 0, right? So the results we have now, if we have equal masses, right? So if we have equal masses, you'll notice that these 2 numbers are equal and they're minused. So we can see there that this will lead this part to be 0, and that will mean that v1f is 0. And if we look at that, if the 2 masses are equal, right, this will be equal to 2m over 2m, right, which will cancel. And so v2f will this will go to 1, and v2f will equal v1i. All right? So hopefully this result makes sense. If they're equal masses, you can see what will get simplified. Now, let's go to the next one. If m2 is much, much bigger than m1, right? So if m2 is huge, the first object's just going to bounce back with the speed mostly unchanged. So just get something opposite. So when you have that, let's see what happens here. So v1 final, right? m2 will be huge. So m1 minus m2 will be approximately, in this case, m1 minus m2 will be approximately minus m2, and m1 plus m2 will approximately be m2. And then so when you look at this, so then if I delete this part, so then what we can see from that previous work is that this fraction goes to -1. And we can see that the speed is just, the direction is just changed, right? You go from moving one way to moving the other way. All right? And v2 final will probably be pretty small. You'll notice that you have a very big number, m2, on the denominator and a very small number upstairs, so you'll have a very, 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 very small velocity. All right? It'll essentially be 0, approximately 0. Now, for a massive projectile, so in this case, if v1 is final is approximately equal to v1 initial, and v2 is equal to 2v1i, the first object keeps going, and the target flies forward at about twice its speed. Okay? So that's our third resulting area from the system. But now we don't need to limit ourselves to the state where we only have a target hitting a stationary target. We can look at 2 objects moving with initial velocities and then colliding and having final velocities. And the procedure for solving the algebra is the same, but man, is it long. So we're just going to look at the results here. All right, when you use energy and conservation and momentum conservation, you can easily get, well, tediously, but not difficultly, with little difficulty, get these two results, right? And so you'll see that the final velocities are in terms of both the initial velocity of both particles. All right. So let's see here. It says, what is the linear, this is again one of those ones where I thought I took off the answers, but I guess I did not. Okay, so I got that one right. So let's try this checkpoint, and this is where we'll end for the day, because I want to do 2D collisions. Yeah, I want to do one 2D collision example, and I don't have time to do it. So that'll be a good place to start tomorrow and review this and bridge to the next chapter. So let's look here. So it says, what is the final momentum of the target in 918, right? If the initial linear momentum of the projectile is 6 kilogram meters per second, and the final linear momentum of the projectile is A, 2 kilograms meters per second, minus 2 kilograms meters per second, and then C, what is the final kinetic energy of the target if the initial final kinetic energies of the projectiles are 5 joules and 2 joules respectively. So I'm going to solve this one at a time. So it says, what is the final linear momentum, right? And let's look at the figure. Yeah, I mean next Thursday. Yeah, by tomorrow, I mean the next time we meet. So if we look at the figure, 918, so 918 is going to be the issue here where we have a projectile moving to a stationary target. Okay, so we know that. So now let's look here. So here we have the initial linear momentum of the projectile is 6 kilograms meters per second. So we know that M1, no, we need a different color. I can't see the blue. We know that M1 V1, right, is equal to initial is equal to 6 kilograms meters per second, right? So we can call that P1 even. P1 initial. All right, so it wants to know the final linear momentum of the projectile. So what it says, what is the final linear momentum of the target if the final linear momentum of the projectile is 2 kilogram meters per second, right? So we know that Pi of the system is equal to 6 because we're going to a target, right? So then we have that Pi equals Pf, and we know that this is equal to, Pf is equal to the final linear momentum of the projectile is 2, right, plus P target, it's going to equal 6, right? So if we solve for PT, it's going to equal 4. Ta-da! And you'll notice that part B is pretty trivial. You just turn this 2 into a minus 2, solve for PT again, you get 8, right? But now let's look at this part C. What is the final kinetic energy of the target if the initial and final kinetic energies of the projectile are 5 and 2 joules? Well, remember, we have fundamentally a projectile with some velocity hitting a target here. So when we look at the initial kinetic energy, or the initial energy, right? It's all kinetic. We have K1 initial plus 0 equals K1 final plus K2 final, right? So we can see here that the final kinetic energies of the projectiles, it wants to know what is the final kinetic energy of the target if the initial and final kinetic energies of the projectile are 5 joules and 2 joules, respectively, right? So that reduces this, the left side of the equation, to 5 equals 2 plus K target, right? Final. And so all we have to do is solve for K target final, and that implies that K target final equals 3. So the math is super simple. It's just setting it up and understanding when to plug in things and how to plug them in. Okay? So that's good for today. I'm going to stop the recording so that it can process.